Hello everybody, it's Tarun. Welcome to your 18th tutorial in the Signal System and Control course. In the last tutorial I taught you the convolution property, okay, and moving forward with that property I'm going to teach you the multiplication property, the duality property and linear constant time difference equations in this unit. Okay, so analogous to the continuous time case, the multiplication property here is same, okay, but there is slight difference. Okay, if our output y of n is multiplication of two input signals x1 of n and x2 of n, so their Fourier transform y of e to the power j omega is 1 upon 2 pi integration over time period 2 pi x1 e to the power j theta multiplied with x2 e to the power j omega minus theta in d theta. Okay, so it is convolution for the continuous time case, okay, but over a time integral of over a period of 2 pi. Okay, so now let's see the proof. Okay, y of e to the power j omega will be summation n equals to minus infinite to infinite y of n e to the power minus j omega n. I have replaced y of n with x1 of n into x2 of n. Okay, so the x1 of n I can rewrite it by the inverse Fourier transform formula 1 upon 2 pi integration over 2 pi x1 e to the power j theta e to the power j theta n d theta into x2 e to the power j omega naught minus j omega n. So I can rewrite it in this manner where the summation is with x2 of n e to the power minus j omega minus theta into n. Okay, which is the Fourier which is the frequency shifted version of the Fourier transform of x2 n. Okay, so now let's see some example. The first example is x of n, where x of n equals to sin pi n by 2 into sin pi 3 pi n by 4 upon pi square into n square. Okay, I can write the x of n as product of two sinc functions in this manner. So from the multiplication property, x of e to the power j omega will be the periodic convolution of these two functions. Okay, so as you all know that the convolution of a sinc function is a rectangular pulse. So for the x1n and x2n, I'll get these two rectangular spectra respectively. Okay, and the or what can I say, the periodic convolution of x1 and x2 will be the desired output y of e to the power j omega. Okay, so you can see here that the aperiodic convolution x of e to the power j omega will be this. Okay, so this is the our first Fourier transform of x1 and this is for x2, and this is the final result with the multiplication property. So now let's see the next property, which is the duality property. Okay, so since there is no formal similarity between discrete time Fourier transform and its inverse, okay, so there is no duality property as it was in the case of continuous time. However, there are similarity between discrete time Fourier series equation and discrete time Fourier transform. Okay, as you all know that the discrete time Fourier series representation of discrete time signal is this. Okay, and its Fourier series coefficients are these. Okay, so I define two periodic sequences. Okay, one is g of n and another is f of k, and the Fourier series representation of g of n is f of k. So if I change the roles of k and n in Fourier coefficient series equations, okay, these equations, then f of n will be kept 1 upon n. Okay, f of n will be 1 upon n. X of n will replace by g of k e to the power minus j k 2 pi by capital N into small n, and which will be equal to 1 upon n summation g of minus k e to the power j k 2 pi by capital N into small n. So we find that f of n, its Fourier series representation is 1 upon n g of minus k. Okay, so with the duality of properties of discrete time Fourier series, there are few properties. The first property is time and frequency shift. So for x n minus n naught, the frequency series representation will be ak e to the power j k 2 pi by n into n naught. Okay, or if I multiply such a complex exponential with x of n, then its Fourier series representation will be ak minus n. Okay, so now let's see the convolution and multiplication property from the duality property. For summation r over period n, x of r into y of n minus r, it is a periodic convolution of x and y, and its Fourier series representation will be capital N into ak and bk, where ak and bk are the respective Fourier series representation of x and y. Okay, so and if I multiply two signals x of n and y of n, their Fourier series representation will be periodic convolution of ak and bk over period n. Okay, so there is a example which you need to do by yourself to find out the similarities with the properties which I have told you. Okay, and this is one example which I am going to tell you. Okay, we are having signal x of n as sine pi n by 2 upon pi n, which I can rewrite in the sinc function notation 1 upon 2 sinc n by 2. Okay, so we are having a continuous time signal gt with period t equals to 2 pi and Fourier series coefficients ak is equal to x of minus k. So g of t will be 1 for mod t greater less than equals to pi by 2. You can refer that example in chapter 3 page 74. Okay, and ak is 1 upon 2 sinc n by 2, and which is also equals to a of minus k, and it is equal to x of k. So from the duality property, the Fourier transform will be x of e to the power j omega, g of omega, where t is replaced by omega only. So to verify this answer, now let's see that gt and find out its Fourier series representation, which is ak. So ak is equals to sine pi k by 2 upon k pi, which is equals to 1 upon 2 pi integral from minus pi to pi gt to the power minus j k t dt. Okay, after I solve this equation, I'll get the desired result by solving this equation also. Okay, which states that x of n has Fourier transform x of e to the power j omega. So this is the summary for Fourier series and transform expressions. Okay, and this is for continuous time and it is for discrete time. So you need to keep one thing in mind, that continuous are aperiodic and discrete periodic. So now let's see the last topic in this unit, which is frequency response and linear constant coefficient difference equations. So recall the discrete time system description by linear constant coefficient difference equations from the unit 1, which was this. Okay, so if we are now talking about the frequency response h of e to the power j omega, apply x of n as e to the power j omega n and as input, and our output y of n will be h of e to the power j omega into e to the power j omega n. Or alternatively, we can try that with the help of convolution property, which states that h of e to the power j omega will be y of e to the power j omega upon x of e to the power e to the power j omega. So if I apply the Fourier transform to the difference equation, okay, plus linearity and time shifting properties, so it will give us e to the power minus j k omega y of e to the power j omega and e to the power minus j k omega x of e to the power j omega, and other things will remain same. And consequently h of e to the power j omega will be summation k equals to 0 to m bk e to the power minus j k omega upon summation k equals to 0 to n ak e to the power minus j k omega. So here are a few things to observe, that h of e to the power j omega is obtained from the difference equation by inspection. Okay, and it is a rational function e to the power minus j omega. Okay, so now let's see examples. First example is where discrete time LTI system is characterized by this equation. So the frequency response will be y of e to the power j omega minus a into e to the power minus j omega, y of e to the power j omega is equal to x of e to the power j omega. So the h of e to the power j omega will be 1 upon 1 minus a e to the power minus j omega, and its impulse response will be a to the power n u of n. Similarly, you can find out the frequency response for the second example. Okay, so now I have taken an input x of n, which is 1 upon 4 to the power n u of n, and I have taken the system of previous example, which means that my h of n is this function. So our output will be h of e to the power j omega into x of e to the power j omega, so which gives us this expression, and whose which is in the frequency domain, and I want to find the output in the time domain. So I'll write it in the partial fraction expansion. Okay, and I can find the value of the constant b11, b12 and b21 by solving the equation, okay, as I told you earlier, and by solving this equation these will get simplified, and it is of the term of a to the power n u of n. Okay, the first one and the last one is of this term, and the middle one is of the n plus 1 e to the power minus j omega n type term. So with the help of frequency shifting property, and not the frequency shifting property, by the help of differentiation in frequency domain, you can find out the desired output of the middle expression. Okay, and with this unit I have also attached an assignment. So as I always suggest that you need to do the assignment by yourself, do not copy from the book or somewhere else. Okay, and if you do it by yourself, then you will find very easy to understand the concepts of this course. So thank you guys for watching. I'll see you in the next tutorial.